All right. So if you go to Canvas, I just uploaded a new file called multiple linear regression. This is the file we're going to be using today when we start using Minitab. So if you want to go ahead and get that and make sure that you've got a Minitab up and running and already signed in, that would be nice. When we start looking at the data that's in here, a couple things we need uh, to try to figure out is what are we making this model for? If we're trying to find, uh, say, drivers of whatever it happens to be, what we want to do is find as many or potentially all variables that we can look at that help us explain why we get an outcome of choice or why we get a particular outcome. Another thing that we can do with some of these models eventually is actually look at trying to make predictions. For this, we need to find as many variables as possible. That help predict are going to help us out with whatever this prediction happens to be to make an accurate model or help out with the accuracy. Sometimes these types of models are the same thing, sometimes they are not. Makes it really, really annoying if you're told that you need to do one type of thing and you end up doing whatever it is, and all of a sudden they're like, that's not going to work. Uh, if you talk with a lot of, say, professors or students that are taking machine learning classes and stuff like that, they're almost always focused on predictions. They don't really care what variables are used to make those predictions as long as it makes their numbers look good. However, uh, suppose you work at a company and your boss realizes that a lot of customers you had, say, 6 months ago aren't there anymore. When you have customers leave your company, that's called churn. Do you think your boss cares more about predicting whether or not a current customer is going to leave or why all those other customers have already left? If you if they're interested in will this customer leave us, we want to make predictions. If they're interested in why they left, so perhaps you can make some changes, get those customers back, then you're interested in what are the drivers of customer churn, which means we need to know what variables we need to select, or well, variables to look at. Once we know what those variables are, we can then start looking into it. We'll actually use prediction or response optimizer today, so you can see or get an idea about what we need to do if, say, we want to increase whatever our outcome is or decrease whatever the outcome is. Because if the outcome, like next week, we'll deal with the logistic regression. If the outcome we're looking at is does a customer churn, A one would be they left you, a zero means they're still with you. So you want to minimize y because zeros are good, ones are bad. So we've got all this stuff that we can play with. We've got all the stuff that we can use. The thing we need to do is figure out what variables are we actually going to be using? What variables belong in the model? I was talking last time about spurious correlations. So again, these look important or statistically significant, but they're not. If we're using real data, unless you're God, you do not know every reason why you get the outcome that you do. Since none of us here are God, the best we can do is try to figure out, or based on what we have, what seems to be creating these issues. With the data that we have, there are 50 variables, and then there's a bunch of y's with like an underscore and then s, and then there's a number after that. What we're going to be doing is looking at y underscore s and then whatever number it is. We're going to see if it's a function of all of these different variables. The way that this data is set up, I made the model, so I know what belongs and what doesn't. And what you're going to, with the model, when you look at the variable names, there's R1, R2, R3, R4, R5, and R6. When we start looking at the data, when you start doing these analyses, what you're going to find is that you might only get 3, 4, 5 of these 6 variables as showing up as being statistically significant. You're going to find a bunch of the WN variables are also going to be popping up. The R stands for it's the right variable. W stands for it's the wrong variable. And what's going to happen once we start analyzing the data, every single one of you is going to have different answers as to what the computer thinks or what the software thinks or what the algorithm thinks is the most important variables. If we were in a typical stats class, probably wouldn't be giving anyone something with 50 variables on it, just because we're going to be looking at a full model, then we're going to be reducing that model to hopefully only the variables that seem like they're statistically significant. And we're going to look at terms that have quadratics and two-way interactions. And going through probably about 250, 300 variables and eliminating 2 or 3 of them at a time is going to take forever. Technically, if you were in a stats class, that would be the way that you do it. You look at the p-value, whatever has the highest p-value, you go back in, you reanalyze, and you delete that one variable, reanalyze, look at the next thing that has the highest p-value, eliminate that, eliminate, eliminate, eliminate. We're going to use a couple different methods that are automated. There are some times when using these automated methods are not the best idea. However, if you get into the data science class, you start taking a machine learning, they're going to be using automated methods similar to these. The methods we're going to look at And I'm going to run through some of these quickly, then have all of you use one of these methods eventually. But the methods we can look at in Minitab are forward, backward, and stepwise. With forward, what happens is we choose the best variable. Then the next variable, and then we repeat that step over and over and over again until we've met some sort of criteria that we set up uh, in the computer. With backward, we start off with that full model. So like 200 plus terms. And then eliminate one at a time. With these two methods, and even when we compare them against stepwise, which is just basically going back and forth between forward and backward. What ends up happening is you could end up with the exact same model. It is completely possible that all three of these will give you the exact same model and tell you, okay, this is what, based on your data, this is what we should be using. It's possible that all three of these methods will give us slightly different models. Part of the reason for that is uh, when we look, or a way to think about how terms are selected and how all these things end up in a model, what we can do is if we think about, say, that box is all the variability that's in the data, and we just start drawing some circles in here. Each one of these circles shows the amount of variability that certain variables actually account for. Clearly, the larger the circle is, the more important it's going to be because it sucks up more of the variability. The way that I've drawn all the bubbles on here, there is no overlap. So with all of these, the VIF for each one of these is going to be 1. And this is essentially the best outcome that we can ask for. However, with some of the models and some of the things that we use in Minitab and with the real data, you might actually have a couple different variables that overlap like that. This overlap increases the VIF that we're looking for. And the higher the VIF we look at, the less likely we are to choose one, maybe even both of those terms. So the order in which they get chosen can actually determine whether or not something gets chosen. Just as an example, if we have one variable that goes like this, then we have another variable that this outer circle, I'm going to pretend like it's clearly bigger than the other circle. Can we all pretend along with me? So whatever this outer circle is, since it's bigger, it's basically more important than this other one. But if we choose the second, this circle first, the importance of the second circle is only going to be this stuff out here, so it might not actually come up as being all that important. even though by itself it's more important because of that variance inflation factor, we're going to have a harder time actually seeing it. So when we're looking at all these different models, some of the things that we need to keep in mind when we look at the different metrics, we need to make sure that the residuals that we're looking at are normally distributed. And I actually went through and checked out this data, played around with it a little bit yesterday. And yes, we are actually going to see or have enough data to really determine is something normally distributed. Data needs to be independent of each other because I made this data, I set it up in a way that each row of data is going to be independent, and there are 25,000 rows of data in here. We want to make sure that the VIF is below 5 whenever possible. What we're going to find is that depending on literally what buttons we click on, we can get very different outcomes, and those outcomes can have very different variance inflation factors. And then we're going to look at the full model, and that's going to be all the x sub n. So everything in what we would call a linear term, x squared, so quadratics. And then say two different variables multiplied by each other. These are going to be the interactions. And just because with these analyses, especially with Minitab, we can do the analysis part really, really quickly. So again, if you're doing this for real, if you're working at a company somewhere, getting the data that we're about to use can take hours. The analysis of the data usually takes minutes, okay? So, does everyone have Minitab up and running? Does everyone have the data set imported? So, if you've never done it before, with Minitab, you can copy and paste everything in, but because of the size of the data that we have, there might be some issues transferring everything over just because of file size. But if you took that Excel sheet and say put it on the desktop or put it into your personal folder, should be able to go to File and then Open. On my computer, I've got it on my desktop in my DS302. So once I've selected on that, I can go ahead and click on Open and everything will work fine. For some of you, you might need to go through a bunch of these things over here to get to, say, your personal storage space on the computers, that system we have here. So I'm going to go ahead and click on Open. This has given me an idea of what the data actually looks like. And it's usually a good idea to check this stuff out just to make sure that everything is working the way that we want it to. So I'm going to go ahead and click on OK. And there's my data. Oops, probably a little bit too big. Now, once I've got the data, I can go over to Stat, Regression, Regression, and then Fit Regression Model. Does everyone have the data imported or? You broke it, didn't you? Okay. So, an issue that can come up as well. Is anyone else having a issue importing? Okay. So I clicked on open. If you look down here, you may have to change the file to say Excel file. There is this drop-down menu here. You can say look at all files if you want. If you look at Excel files, uh, that might be an issue. This is a Microsoft Excel worksheet, so that could be an issue. Is it working now?
Yeah.
Are you trying to say uncorrupt or corruptible? Yeah, I am. And I forgot to mention at the beginning of the semester, I do take bribes. $1 million for the first 50%, $250,000 for every extra 10%. So if anyone can cough up 2.25 million, I'll give you an A. Anyone? Ah, why can't I teach rich kids? All right. So anyway, if you actually have the data, you can go to staff regression. The predictor we're going to look at is, I think it's Y underscore S5. And then all of the R's and all the W's. Those are going to be the continuous variables we look at. So you just completely broke it, didn't you? So what happens if you click on that? Always part of the fun of the doing stuff like this. Thank you. So her computer, she clicked on the file, it went to like say the preview page. Then she tried to download it from there. If you go to the actual file, and then instead of trying to open it, just download it from the files. All of a sudden it works. Now it's working. So I'll get you a sec. Okay, so thanks to Doug there. That's where it's on the download. When you do that, it doesn't actually work. You slide it over to the desktop. Okay. So now where it says action. Now it's 3,000. 3,000.
Yeah, sometimes there's nothing like that. I know when I'm teaching at, public community college, you can't download any. It's hard, like downloading. So like, so it. So literally, if you have a flash drive, you can take it from the on the flash drive, save on the flash drive. Then try to open it from the flash drive, into whatever. And go check it. And it works. So. You have to say that people are here. Okay. I hope you'll say something important. Open. Okay. And dealer. That's a good idea. All I need is it's still like packing what you download. Yeah, these stuff. It's like a totally different name now, but I'm putting on. No, it works. Everyone else got it downloaded? Okay.
So is anyone familiar with FOPO? Bluff around and find out. Yeah, no? So now that we've got our data imported, so again, I'm going to go to stat, regression, fit regression model. My response here is going to be this y underscore S5. My continuous predictors are going to be R1 through W44. And the model that I'm going to create here. So once you've got all these in, and I will say too, the way that Minitab is set up, if you notice, it says responses. So it's completely possible that there might be 2 or 3 different variables you want to try to model simultaneously because they're related to each other. For example, if you're an engineer and you're creating a new or looking at a new engine design and you want to say maximize horsepower, but you also need to be conscious of, say, wear and tear that's going to cause, as well as, say, fuel efficiency. You can actually model all 3 of those things simultaneously, assuming you have all that data. And then with the response optimizer, you can actually then come in and say, I want to maximize horsepower, say, while minimizing wear and tear and maintaining a MPG of whatever it happens to be. So once I go to model, literally just going to highlight everything that's on there. And then it says terms through order 2. What this is going to do is it's automatically going to create every quadratic term and every interaction term. So once we've got that, you can go ahead and click on add. So now these are all the different variables and variable combinations we're going to be looking at. And if you're looking at that and thinking, wow, that's a lot, that's why we're going to be using some of these automated methods, because going in and clicking off of 1 or 2 at a time over and over and over again, dear God. I'm going to go ahead and click on OK. Options. Again, we're probably not going to need anything that's in here. So I'm just going to go ahead and click on all OK. Coding. For right now, I'm going to leave everything as it is, just so we can see what happens here. Stepwise, when we click on the top here, it says method, none. Now we have stepwise forward selection, backward elimination, Forward information criteria, selection with validation. Let's start with forward selection. So we've got all of these potential terms, and it says alpha to enter. I'm going to change that to 0.15. Then I'm going to click on OK. Validation here. We all like validation, right? So where it says validation method, the bottom one here, and I apologize that this is so small, but it says validation with a test set. So our third option here. And it says here, randomly select a fraction of the rows from the test set. The test set is, or as the test set, what's going to happen is whatever value we put in this first thing here, which is already set to 0.3, so it's 30%. 30% of the data is going to be randomly withheld from the model or from the software looking at it. Once the software thinks it has a viable model, it's going to start comparing predictions and doing all sorts of other calculations to see how well the model it just made does with this new data, which is something that in a traditional stats class we were never taught how to do, but it is very, very useful for what we're doing. And right now, it says base for random number generator. It's got it as 1, 2, 3, 4, 5. Because I want everyone here to have a different, this is the random seed that I was talking about. Because I want everyone to have a different random seed. Use of 4 digits that is going to be unique to you. So if you're like, hey, I'm going to use my birth year, how many other people here will have the same birth year? So like the day of your birth, the month of your birth, the month of your birth, day of your birth, however you want to do it, that would work out well. So I was born on March 12th. So I'm going to put my random seed as 0312. And I'm hoping that no one else in here has a birthday that's the same day as mine. So if you want to put the PIN that you use for your debit card, go right ahead. I'm not going to look. Really, I'm not going to look. So just the birthday, birth year, or sorry, a birthday, birth month, birthday, however you want to do it. As long as you've got 4 numbers that are different from everyone else. So choose whatever. Going to come down here and click on OK. Graphs, again, we want a Pareto chart. And just because it's convenient, do the 4 and 1. And then click on OK. Results, be fine. Storage will be fine. And now I can come up here and click on OK. You see processing. So how long did that take? Oh, it's still, so maybe under a minute, hopefully. So what I'm left with is after, or by using this forward selection thing, I am left with this table. And you can see that it screwed up on some of these, so might need to tap that over just a little bit to make it look a little bit better. But essentially, Oops. The column that I've got right here is all the different p-values. Some of these are going to have p-values that are above the 0.05 that we normally look for. Part of the reason the software does that is if there seems to be a statistically significant, say, interaction term here, from the point of view of the traditional stats class, you keep the lower level term, so that linear term, the R1 through R6, W6, W10, 12, 13, 40, and 41. Even if those by themselves have a really large p-value, if it's used in an interaction somewhere, you keep the linear term in there. And you can see that W13 is part of an important interaction term. And when you look at the last column here, what is that? VIF. Do those VIF values actually look below 5? Are any of them actually below 5? Okay, I got a couple of them right there, so I've got 3. So what I can tell from this is even though it's telling me that all these different variables are actually statistically significant, somehow, because of that VIF, I am highly concerned about the results. I'm going to get rid of that. No, don't save that. You can see fits and diagnostics, unusual observations. It's trying to tell you, hey, anything that's got the X here, oh, that's an extreme outlier. Well, we've got 25,000 data points. We should expect 5% of them to be, or between 1% and 5% of them to be extreme outliers. And you get to scroll through. Come on. Let's go. So looking at what we've got here, with the other data sets we only had, what, 30, 40 data points? So asking questions like, do you see a bell-shaped curve? Do all the points actually line up? So this is what, for trying to figure out, does the data look like it's normally distributed? Do all the blue dots look like they basically line up on the red line that you can't see because the blue dots are so close to the red line in the first place? So this is telling us that the normality idea seems to be working. When we look at the histogram of the residuals, do those look like bell-shaped curves? Finally, we have a bell-shaped curve that looks like a bell-shaped curve. So that's a thing. That's definitely a thing. Because we've got so many data points in here, it's really hard to try to make anything of this. So moving on. Looks like someone used a bird shot on a target, doesn't it? Just from a shotgun. So that's also a thing. We've got some data points that look like they might be a little bit different than others, but again, 25,000 data points. If 1% of the data is, say, an extreme outlier, how many data points should that be? So when we're looking at these, we have to keep that sort of thing in mind. Based on all this, it looks like the model does conform to the idea of the normality distribution. The independence of the data looks good to me because I can't tell anything different by looking at this. The VIF for a lot of my terms is above 5.0. That is concerning for me. Well, I did get a full model, or we did go from a full model and reduce it. So I'm gonna, just so we can see how things change when we're going through, I'm going to save that to Word. Just because we're trying to get used to this. So if you weren't able to follow along with to get this data, we are going to do this again. So go ahead and hit the stat button, regression, regression, fit regression model. We're again going to use that y_s5. We're going to look at all those variables again. Click on stepwise. So we used forward selection the first time. Let's use backward elimination just to see what's actually going on here. Everything else should be the same. So I'm going to go ahead and click on OK. And everything else down here should be the same. So I'm going to go ahead again and click on OK. And we wait. And we wait. And we wait. And we wait. So it says the following terms cannot be estimated and were removed. So looks like it got rid of a bunch of them. All right, whatever. Sometimes you will get error messages like that. Is it actually true that those cannot be estimated? Actually, no. So it looks like my software may have choked on something. But coming back and looking again, what are the variables that the software has decided are statistically significant? What are the VIF values for all of these? So again, these are all really, really high. But this time it's telling me didn't want to do that. Open in Word, not PowerPoint. Go away. Don't save. Open in Word. So you can see all these extra terms that were found to be statistically significant. And it looks like most of the what we would call the linear effects, so R1 through R6 and W1 through W44, seem to be important in some sort of a interaction term or quadratic term or something like that. So that's very different from what we got when we did forward. When you do the forward modeling, you pick the most important one, then you pick the next most important, the third most, fourth most, fifth most, until you've met whatever criteria it is that you're working with. With backward, you look at everything and you eliminate things that you don't need. So right now, our choice of doing a forward versus backward, completely different models, completely different answers coming up. Sometimes that happens, sometimes not. Going to do this one more time, just show everything that's going on here. So regression, 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 fit regression model. This time for stepwise, I'm actually going to make it stepwise. So once I've got that, I can click on OK. I can click on OK. I'm processing this. That seemed like it went a whole lot faster, didn't it? And it's not giving me any errors trying to tell me, oh, we can't deal with these terms, blah, 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 whatever. And we can see that we've eliminated a lot more of the variables using this stepwise process than we did the backward process. But we still have the really large VIF. When we look at the graphs at the end here, clearly you can see which variables seem to be the most important here. So we can use this information to try to come up with a particular model. Now, because of the high VIF that we just had, we want to go back to where it says coding. And I'm going to change that from do not standardize to just subtract the mean. And then click on OK. For this, I'm just going to keep everything as it is. Or let it do its thing again. And look at the VIF on every single one of these terms here. What did I say the best value for this was going to be? 1. What's the highest VIF I have here? 1.01. Awesome. So I already know that we're going to have normal distribution. I know the data is independent. I know that the VIF for all these terms is below 5. We use the full model and we've selected essentially the best variables to look at. And with this particular data set, got R1, R2, 3, 4, 5, 6. Those are the variables that I intentionally put into the model. W6, W10, 12, 13, 40, 41. That's what I got. Your results will be different. So if you're looking at what I have up here and you're like, mine doesn't look like yours, that's the point. But we can see that all those W variables that we have, those are all spurious correlations. Since we know what the model actually is, we see all these W's, we know that they don't belong. But when you're doing this for real, what's going to happen? You don't know what belongs. You don't know what does not belong. And one of the data sets that I'm going to give all of you to work on next Thursday, we're going to try to predict, does someone have heart disease? And we're going to look at 7 or 8 variables where if you follow medical advice, all claim that could be important for determining whether or not you have heart disease. And I don't think anyone in here is actually going to find that everything that we think of is actually going to be important for that. Like one of the variables is smoking. If you look up on Google, does smoking cause heart disease? It's going to say yes. That's a well-established fact. But some of you, when you look at the data, smoking is not going to be chosen as an important variable. So with what we've got here, what I would like for all of you to do, and you're going to have to write these down. So hopefully everyone got to this point where we have y underscore S5. What I did here is I said the variability of this data is 5 units. That's what the S5 stands for. So write on a piece of paper, write down all the variables that you found, and then come up here and write them up on the board. So for me, R1, 2, 3, 4, 5, 6. 6, 10, 12, 13. Forty and 41. When you get them, we got other markers up here. I swear I showered this month. I don't smell that bad, do I? Hmm? So, right there. The R1 through 6, 6, 9, 10, 13, 45. Just, and when you're looking at them, like I've got R1, 2, 3, 4, 5, 6, W6, W10, W12, W13,
Can we just pump this up?
W40, W41.
Yeah. Can I do over?
Yeah.
Yeah. What is?
Well, that's just telling you. What you need is right there, so you have R1 through R6, W6. Yeah. Thank you. Okay, all right. Right. Yeah.
Are there any marker right there for you? Got one more marker. And with the stuff that you guys are writing down, the only wrong answer is here is if you lie about something. So if your answers are totally different from someone else's, that's part of the point. Don't be embarrassed or write it down. Okay. Got another couple markers down here. Can do a blue one or a green one right there.
Anyone else have?
You might need to walk up here and look at this, but is anyone noticing really weird things? We all agreed R1 through R6 belong. Cool. A lot of us wrote down W6 So W6, 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 W6. I got W6, W6, W6. They didn't. Oh, someone's an outlier. No, it's fine. W6. They didn't get W6, they did. Couple people there got W6. So what we just did here is called an ensemble method. One of the things we can do with all of this information is we can now look at what everyone said is actually important. We have 50 variables. Did anyone write 50 different variables up here? Are there variables that we've all decided do not belong in the model? Just looking really quickly. W1, W2. No one says it's important there. W1 and 2 not important there, not important there, not important, not important, not important, not important, not important, not important. Okay, we got one vote for W2. One. Looks like it's really okay, and we got one vote for W1. So out of the 50 variables and out of, say, the 20 students that are 30 students or however many that actually wrote this stuff down, one of you thinks W1 is important. One of you thinks W2 is important. Do we think it's really important, or do we think that's more of one of these spurious correlations, something that looks like it belongs? It looks like we should be using it for something, but maybe it's really not. Yeah, 1 out of 30 people. But what we can do is look at this and pretend like, say these are doctors' opinions. We've got 30 expert doctor opinions. One of them said, yeah, that's important. Everyone else is like, no. Can we eliminate that one? Can we say W1 is not a statistically significant variable? We've got one vote for W2. There's some votes for W3. I don't think anyone chose like W 42, 43, and okay, we got 142 to no 43s and 44s. So 0 out of 30 opinions say W 42, 43, and 44 are important. So we know that they're not. And when you go and you do your analyses, if you're doing it, say for whatever company it is, this is the type of thing that's going to come up. This is going to happen all the time. Your model is going to say one thing. Their model is going to say something slightly different, possibly majorly different. How do we know which variables we should be using? If we all agree that the variable was chosen by, say, 80% and above, that variable is important. We can now go back, look at all the variables we have, eliminate the stuff we all agree doesn't belong. So get rid of a W 42, 43, 44. Get rid of the like W1 and W2 because they only came up one time each. And we have done something called, in data science, it's called feature engineering. We've also found potential drivers. We can also think of this as, say, like a sports bracket. Everyone's competing against each other. Who are the top competitors? Well, the top competitors are the ones that come up the most often. Once we know who the top competitors are, we can go back and basically eliminate all of those variables from contention, then run this model a couple more times and try to refine it a little bit more. Assuming that everyone here has a different birthday and that's what your random number was, we could do this over again. We could probably get away with eliminating some of these W variables. Uh, with the data that we've got here as well, the variability that I put into this model is 5 units. Let's go back. Going to do this one more time. Stat, regression, regression, fit regression model. This time our response is going to be the y_s50. So there's a lot more variability. There's a lot more noise in this data. Going to keep everything else the same. And then I'm just going to click on OK. And it's processing, 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 processing. So scroll down. And I will say the model that I put in here is exactly the same. The only thing that changed was the amount of variability within the data. Originally, this is what I said was important. If you look at what I've got now, I still agree on R1 through R6, but 14 and 17. So I've eliminated a bunch of these. And I'm assuming for the rest of you, you still have R1 through R. Did anyone say lose one of the R values when they did that? Because when I was playing on it last night, I actually lost R6 in a couple of the models that I did. Which means I know R6 belongs, but because there is so much variability and because of the way the random seeds were set up, R6 did not appear as a statistically significant variable. It's part of the model, but it's not in there. And when we're looking at all this stuff too, with very small amount of variability, we see a whole lot more of these spurious correlations popping up. When we've got larger variability, these spurious correlations actually don't pop up as much. If you talk with some of the statisticians like I did about that, they looked at me and were like, dude, that should be the opposite way. Why? Because if there's a lot of variability, you may have certain values that all of a sudden, because you've got 2 or 3 outliers and extreme outliers, makes it look significantly more important. We're finding no. When we have larger variability data, we actually get less of these spurious correlations. And again, I fully expect every single one of you to have slight variance on what I found. So if you get into the data, what is it, intro to data mining class 325 or 310 or 310 or 325 or whatever it is, with the Dr. Kaufman, you end up using some of these or methods that are similar to this called ensemble methods. And basically what we're seeing here is we can use everybody's opinion and everybody's well-educated opinion, eliminate a lot of these variables, put them, say, back into the model, let them fight it out for, say, a second round or a third round or something like that. And hopefully, eventually, we can determine how many variables, or determine, sorry, which variables are actually important for the model. Like I said here, I know that R1 through R6 are important because I made it that way. But I've got all this other stuff popping up saying, hey, look at me. I belong too. So when you do this for real, when you get into machine learning or what all those other fun classes. A lot of times what they do is they only take the information that you got. So one person's data, and then assume that that one person got the right results. And then they try to optimize that one person's model. What are we finding here? No one agrees on what that one model is, right? We can all agree certain things do belong. We can all agree certain things do not belong. But just looking at what we have here, this, for those of you that were at the talk that I gave to the math department, what you all did for me is basically what I did to make every single one of those slides. So thank you for getting me a whole lot more data really quickly. You know, I'm not going to write this stuff down, but just to think about it, when we do all these different modeling things, it's all about getting, say, the best model that we can. This is telling us that we're all going to have different opinions on what that model is. And one last thing to do here. So go back up to stat, go to regression, and then the little gold star thing down here that says response optimizer. So suppose for a moment that the Y value we're looking at is, say, daily revenue for the company that you work for, okay? We want to try to figure out what? How to make more revenue or less revenue? We want to figure out how to make more revenue for that company. Go to response optimizer. For YS50, change that to say maximize. I believe everything else on here is going to be set to go. And then you can just click on OK. And what we've got here so with that last model that I created, that's the one that it's using to do this. It says, according to this, the best I can do is 1,863.93. How do I get there? I set R1 to 73.2798, R2 to 73.2798, R3 77, R4 88, R5 and R6, set both of those to 1. W14, make that 18. W17, set it to 0. Because we're using data that I made up, what does any of this actually mean? Absolutely nothing. But again, let's say you're an engineer, you're trying to create a new, or you're looking at an engine and you want to say maximize horsepower. Each one of those variables up there is going to be something that you can actually go back and physically change. And you might have, say, how much air do you need to go into the cylinder at any one point? How much fuel? And all these different, how many milliseconds offset timing on blah, 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 or whatever. And then it's going to tell you how much horsepower things you can make on that engine that you've got. And again, if you happen to be working for a smaller company, back when I was a student here, my fiance worked at Arby's down in Allen Park off of Southfield. And at one point, one of the managers there realized that somebody was stealing money. Well, you could go back, you could look at make Y, the amount of money that was stolen on a day-by-day basis. All the different variables you have would be, did this employee work? Yes or no? You go back, you do an analysis like this. And essentially, any variable that comes up has something to do with the amount of stolen money. It might be they don't steal money, or it might be they are the thief. So her manager could actually use this, go to response optimizer. If Y is the amount of money that's stolen, what do? You want to minimize that, right? Set it to minimize. And then every number that pops up there is basically going to be, who do you want working for you? If they get a uh, if they get a one, or if they get a one, they are minimizing your stolen money. So let them work for you. If it's a zero, that's how many hours they should be working, because having them work 0 hours minimizes stolen money. Seriously. If our response outcome is taste profile, how many taste points does something get? Probably want to maximize that. So again, response optimizer, maximize. If you have two different variables you want to look at, say increase revenue while having a minimum cost or maintaining cost at a certain level. Because you can have two different things going on at the same time. You can say, I want to maximize revenue and maintain or target whatever a particular value is. Does that sound useful for anything that anyone's going to be doing at any point in their lives in the future? And I was looking at the syllabus, trying to figure out what when we're going to have the second exam and when the finals is. I put the schedule together based on, I asked when the final was and was told, oh, yeah, there's going to be one. Like when? Well, we don't know. Still don't know. So, next week, the stuff that we do, we might end up doing forecasting on Tuesday, logistic regression on Thursday, and then the week before Thanksgiving do the second exam. That way you have extra time after the exam to study for it. Or I might have the day of the final exam off and not have to do anything. I will let you all know. But when we do the forecasting, where do you do forecasting at a lot? Finance, right? What's the stock price going to be tomorrow? How do I make as much money as possible? Regression models and response optimizer. And hopefully everything works out. So you can all go home now. Have a good weekend.
Is it